A 130-meter ferry, lighter than a normal ship of half its length, faster than most warships, carrying cars and passengers across open sea at racing yacht speed. The fight isn't power, it's keeping aluminum straight under heat, holding shape across thousands of welds, then proving it at over 40 knots. We'll walk every step. The finale's worth waiting for. 58 knots sounds like a racing number until the camera pulls back. Francisco was 99 meters long, built for more than 1,000 passengers and 150 cars, and still reached 107 kilometers per hour. A speedboat can remove comfort to gain speed. A ferry carries seats, ramps, glazing, toilets, shops, ducts, cables, safety gear, vehicle decks, and crew spaces. Each item adds weight before the vessel ever meets a wave. That weight is the first limit. Incat answered with aluminum, narrow wave-piercing hulls, water jets, turbine power, and strict weight control from the earliest design choice in Tasmania's yard from scratch. Step inside a fast ferry and the speed problem stops feeling abstract. The bridge carries screens and controls. The passenger deck carries seats, restrooms, lighting, windows, safety equipment, flooring, and service spaces. Outside, the wake makes the vessel seem effortless. Inside, every finished surface adds mass that must be pushed through water. More power does not automatically solve it. Stronger machinery needs stronger supports, cooling, fuel or battery capacity, and maintenance access. Many fast vessel concepts lose their edge there. Sea trials reveal whether the full passenger craft still works as designed. Crews check trim, turning, vibration, acceleration, and handling with real systems on board, not a bare test shell. Real speed comes from matching hull, interior, machinery, and route. The ferry has to remain quick after passengers, fittings, services, and operating rules turn the hull into a working vessel offshore safely every day, repeatedly, with margins for weather and wear aboard. Power reaches the propulsor last, and that final step can waste plenty. Water jets suit high-speed ferries because efficiency rises above 25 to 30 knots. Steering and reversing are built in, and compact units fit narrow sterns. Better cavitation margin protects thrust, range, and comfort. Hull shape now faces judgment too. Why split a ship into two hulls when one hull is simpler? Hull 096 gives the answer at industrial scale. The ferry needs a broad platform for passengers, vehicles, lounges, machinery, and batteries. Yet one broad hull would shove too much water aside at speed. Two slim aluminum hulls reduce resistance while carrying that platform above them. The cost appears between the hulls. Waves lift each side differently, so the cross-deck must carry twisting loads without becoming heavy. That trade-off explains the strange shape, wide from above, sharp underneath, and carefully strengthened where passengers never look during crossings at sea. Dry dock removes the illusion that a ferry is just a box with engines. Bendago Express rises out of the water, and the underside becomes the lesson. Twin hulls, foils, water jet openings, coatings, and vehicle deck structure. Narrow hulls reduce drag. The wide deck earns money by carrying people and cars. At speed, the harder work happens below the cabin floor. Waves can strike the underside. Each hull can receive a different impact, and the connecting structure must stay stiff. Maintenance below the waterline protects the original speed promise. Clean coatings, serviced jets, checked foils, and inspected structure help the next crossing feel smooth under real saltwater schedules, heavy payloads, dockings, weather windows, hurried turnarounds, and night work offshore. 40 megawatt-hours of batteries change the meaning of hull efficiency. In a 130-meter ferry, stored energy is precious, heavy, and route-limited. The hull must protect range, draft, trim, and safety margins at once. Efficient multi-hull geometry becomes part of the energy system, not just the outer shell on board itself. Water jets reveal how sensitive the stern shape is. Direct-driven motors and compact jet units work best when the aft hull feeds them clean, steady water. Turbulence at the inlet steals thrust, raises noise, and reduces range. Advanced propulsion still depends on the hull guiding flow correctly into each unit safely. Watch a bare aluminum catamaran come together and the layout becomes obvious. Two hulls start as separate structures, then large sections are flipped, joined, and locked under one deck. That broad platform is why catamarans suit ferries. Usable space sits above slender hulls. The risk lies in measurement. Hull spacing, deck alignment, and water jet position are fixed long before launch. A small yard error can appear later as trim change, vibration, steering correction, or extra drag. Launch day feels satisfying, but speed was secured earlier, when metal met its designed line without force or guesswork, repeatedly, section by section, exactly. Trimaran geometry takes the multi-hull idea in another direction. A central hull carries the main length, while smaller side hulls add stability and support the wider platform. The Mayflower build shows that shape forming through frames, welded sections, crane moves, and side hull integration. Although this vessel is autonomous rather than a passenger ferry, the visual lesson is valuable. Designers use multiple hulls when speed, deck area, and stability must share one vessel. The side hulls are structural partners. They change roll response, share loads, and widen usable space without forcing the center hull to become a slow, wide body. The difficult part sits in the links. Wave loads must pass through the connecting structure without concentrating stress. Multi-hull design wins resistance and deck area, then pays for those gains with cross-structure, sealed compartments, bulkheads, and alignment checks before sea trials validate the numbers under load in open water later, safely. The yard tour ties hull shape to the hidden safety grid inside it. Cut plates and modules are visible, yet subdivision is the more important clue. A fast aluminum hull cannot rely on low weight alone. It needs watertight compartments, transverse bulkheads, frames, and clear load paths. In a wave-piercing catamaran, each hull may contain multiple sealed sections, so damage or flooding stays limited. Bulkheads also help carry forces from slamming, turning, vehicle loads, and cross-deck twisting. Water jets moving about 21,000 liters per second from each unit add another demand at the stern. The hull must supply steady flow. High-speed shape safety subdivision, and propulsion layout are tied together. A perfect hull drawing can still lose speed in the yard if aluminum shifts, welds pull, or modules land a few millimeters off during production and inspection before launch day, when hidden geometry finally meets water at speed offshore safely. Before the ferry can run fast, the yard has to make flat aluminum hold a curved design. Digital models become millimeter-accurate cut plates, then panels, then modules. Performance can be damaged surprisingly early. Aluminum saves weight, yet thin pieces shift during cutting, lifting, and welding. If frames drift or panels pull out of shape, the vessel may need correction, extra fairing, or added material before launch. The key limit is shape control. Speed is protected by plane precision, marking, nesting, cutting, jigging, measuring, and refusing to bury small errors inside the hull during production. Work every day on site safely. Rollback footage turns the factory into a scale reference. A huge aluminum hull moves slowly while superstructure modules wait above it. The critical moment comes at landing. One deck section out of line can disturb windows, wiring, ceilings, weight distribution, and final trim across the vessel later during trials offshore. Shipbuilding skill is easier to underestimate than crane size. Apprentices learn how aluminum fits, heats, closes, distorts, and cleans up after welding. A high-speed ferry contains thousands of hidden decisions made by fabricators, welders, electricians, pipe fitters, and finishers. Machines cut accurately, but people still decide whether a joint fits, a cable route remains serviceable, or a panel closes without forcing the structure. The fragile part is repetition. A yard does not need one careful worker, it needs hundreds making careful choices across modules, shifts, vessels, and deadlines, while quality stays invisible to passengers at sea later, under load, daily. One module lift can lock in weeks of work. The passenger deck block has to hang level, clear people, meet the frame, and land without forcing the aluminum structure out of line again today. Then, the quietest-looking operation becomes one of the hardest: aluminum welding. Heat enters a narrow zone. Aluminum expands quickly, and thin panels can pull away from their intended shape. The welding system shown here matters because settings stay close to the welder: wire speed, volts, amps, starts, and crater fill. Push-pull feeding reduces wire jams, while preset modes reduce guessing when workers move between thin and thick sections. The heat window is narrow. Too little heat risks poor fusion. Too much heat bends panels and creates rework. A fast ferry cannot carry endless corrections because added metal and extra fairing cost weight. Good aluminum shipbuilding relies on clean preparation, clamping, planned sequence, steady travel, inspection, and correction before compartments close. The shell may look complete, but machinery, batteries, interiors, cables, pipes, and access spaces still have to enter without taking back the speed this structure earned during service offshore safely. Francisco's speed begins with a machine descended from aircraft thinking, the GE LM2500 marine gas turbine. The appeal is power density. A gas turbine can deliver huge output without the weight of a slower industrial engine, which matters when a ferry has to move people, cars, fuel, and structure at speed. The risk is service access. Salt air, sand, and foreign object damage can harm compressor blades, and removing an engine from a ship can cost weeks. GE's split casing design lets technicians open the unit on board, inspect damage, repair blades, and return propulsion power without turning maintenance into shutdown. A gas turbine room is not a clean display case. Navy mechanical technicians describe power runs, fuel checks, blade pitch control, contaminants, and engine troubleshooting. That matters here because high-speed ferry machinery lives under heat, vibration, salt, and tight access. Raw power only helps when mechanics can keep it ready. The electrical side shows a second layer of speed that viewers rarely see. Gas turbines do not only spin, they depend on sensors, generators, load sharing, switchboards, alarms, and technicians who understand what happens when power suddenly shifts from one engine room to another. Too much load can raise temperature and trip equipment. For a giant ferry, controls are the nervous system. They keep propulsion, hotel loads, fuel systems, and safety equipment from pulling the vessel in different directions during every high-speed crossing. Once power reaches the stern, the ferry still needs a way to push water without hanging large propellers below the hull. Water jets solve that by drawing water in from underneath, accelerating it through an impeller, then firing it out astern. Steering happens by turning the jet. Reversing and braking use buckets that redirect the flow ahead. Wärtsilä's modular water jets add high-speed efficiency, compact transom installation, integrated steering, and improved cavitation margin. The hidden gain is draft. Less exposed machinery under the vessel helps fast ferries work near ports, ramps, and shallow routes without sacrificing maneuvering control in tight harbor approaches. Liquefied natural gas, or LNG, turns fuel into a design problem, not a simple tank choice. The Bencomo Express conversion shows why. A 95.47-meter high-speed ROPA-X, originally powered by 4 Caterpillar 3618 engines, was adapted through an external engine test, onboard conversion, and real sea trials. The test engine weighed 35 tons and produced 7,200 kilowatts. The dual-fuel mode used about 90% LNG and 10% diesel. Certification mattered because gas fuel brings ventilation, detection, shutdown logic, valves, pipe routing, and crew procedures. The result was cleaner operation. Reported reductions included 32% CO2, 45% NOx, and 90% SOx. For a 50-knot ferry, LNG adds even more pressure. Tanks, piping, safety zones, backup fuel, and control rooms must fit without ruining weight distribution, trim, access, or service speed. Fuel choice becomes architecture before the ship ever leaves port and before the first passenger ever boards for commercial service safely. Digital planning shows why systems cannot be squeezed in late. Operators need routes, maintenance, controls, breakers, layouts, and energy use modeled before construction. A digital model reduces surprises when engines, water jets, LNG zones, and control equipment compete for space. The ship can still slow before leaving port, Comfort adds weight. Hull 96's shift from LNG to full electric power shows how quickly weight planning can change. Batteries, DC hubs, switchboards, transformers, water jets, motors, and passenger spaces all compete inside one ferry. The hard part is not adding technology. It is adding it without stealing space, access, stability, or route performance. LEO is slower than the high-speed ferries here. Yet its layout reveals the passenger weight problem clearly. 7 decks carry 1,500 passengers, 290 cars, and 35 trucks, while LNG tanks and dual-fuel machinery demand protected space. Every convenience, vehicle lane, tank, pipe, and exit changes how the vessel sits afloat. The broad mission bay begins on land with facilities, workforce, process control, and repeatable aluminum construction. Austal's promo clip points to industrial capacity. Large, fast transports require yards that can build, repair, upgrade, and standardize complex vessels. Empty space at sea depends on disciplined work ashore across every shift safely. The Carson City rollout turns EPF scale into a moving object. A large all-aluminum catamaran leaves the construction hall on transporters, rolls onto a barge, then reaches the floating dry dock where water makes the hull self-supporting for the first time. That sequence matters because mission value starts with volume. The vessel needs wide beam, shallow draft, vehicle access, and a deck strong enough for payload, yet the hull must remain light enough for fast transport. Launch is therefore more than ceremony. It proves the structure can move from factory support to water support without losing alignment, balance, or access. Operational footage shows why EPF space matters. Troops, vehicles, medical support, containers, helicopters, and V-22 operations can share one high-speed platform because the catamaran offers width and shallow draft. The challenge is making open volume strong, accessible, and reconfigurable. A ramp turns the bay into a port connection. The flight deck turns the ship into a moving logistics node for missions far beyond a normal ferry route. EPF-13 shows useful space now includes control code. Its autonomy trials combine navigation, machinery, electronics and electrical equipment, cameras, networks, and cybersecurity on a vessel over 100 meters long. Mission space is valuable only when the ship can move safely through traffic, manage machinery, and keep operators informed. The open bay carries cargo. The final test is whether those systems work together at sea under pressure reliably. Before sensors and alarms can prove anything, the aluminum shell has to deserve testing. The Quintrex plate boat is smaller than a ferry, yet the clue is useful. 6mm bottom sheets, 4mm sides, ribs, stringers, bulkheads, fuel space, and 80 hours of welding turn flat plates into water-ready aluminum structure. MeCat turns trial work into service. A 58-meter catamaran approaches beaches, lowers ramps, unloads cars, carries passengers, and returns with trim under control. Speed counts when shallow approaches and turnaround pressure stay manageable. A 21-meter utility catamaran makes testing practical. The ramp lands cleanly. 7.5 tons of cargo stay controlled, and 25-knot performance feeds predictable handling. Engines, crew space, controls, and low draft need verification. Commissioning depends on a yard that treats testing as part of production, never an afterthought. Austal's process connects design, engineering, supply chain, welding, pipe fitting, final assembly, and sea trial crews. Advanced manufacturing helps, but the valuable step is disciplined handoff. Each system reaches water with documents, checks, access points, and people ready to trace faults without guessing while pressure, temperature, alarms, pumps, hydraulics, steering, and controls start talking to each other properly on schedule. A launch is the first honest contact with buoyancy. LCU 1710 leaves land on transporters, hangs under heavy lifting gear, and enters water under close control. The hull may float, but commissioning still begins. Acceptance trials put hidden assumptions under speed. LCS-5 drives through waves, turns hard, and throws a long wake, while crews watch response, vibration, handling, temperatures, and propulsion behavior. A small trim or control error grows quickly when speed and wave impact arrive together during official testing with sensors running. A vessel can pass the dockside checklist and still be humbled offshore because the sea checks trim, heat, steering, alarms, pumps, and crew reaction at the same time. EPF footage shows why sea trials must test useful work, not clean running alone. The ship has to move fast, launch aircraft, lower ramps, carry vehicles, handle troops, support medical tasks, and operate with boats. Speed matters only when the mission bay, flight deck, propulsion, steering, and crew workflow stay usable together. A transport vessel that looks impressive empty still has to prove it can carry weight, unload quickly, and approach ports never designed for ideal conditions. That is where fast aluminum turns from a performance claim into logistics, with payload, people, aircraft, and pier access tested at once on board. LCS explains a harsher version of system testing. 4 water jets, diesel engines for lower speed transit, gas turbines for over 40 knots, plug-in mission modules, automation-heavy bridge stations, and small crews create a very busy vessel. The difficult part is coordination. Speed cannot replace sensors, maintenance, training, damage control, or reliable power management. When every sailor carries several duties, the ship must make information clear, machinery accessible, and failures traceable fast. High speed becomes useful only when the rest of the vessel can keep up in real operations, with crews, faults, changing orders, tight space, fatigue, heat, and paperwork under pressure. POLA shows a different route from design to useful naval speed. Modular construction across countries, then integration into one working vessel. Sections were built in the Netherlands and Mexico, transported, aligned in dry dock, fitted with superstructure, propulsion, radar, sensors, and deck systems, then sent to trials. The lesson fits here because speed gains value only after integration. A patrol vessel can run offshore only when its bridge, machinery, communications, weapons handling, crew spaces, paint, watertight checks, and turning tests agree with the design. Distributed building can shorten schedules, but it also makes alignment and interface control unforgiving. One module built perfectly in one yard still has to meet another module, another electrical system, and another crew procedure thousands of miles away. Sea trials reveal whether that chain works under motion, heat, vibration, command pressure, and saltwater exposure after launch with real operators aboard at sea, together under tight deadlines. The OPV clip moves from pure speed toward endurance and reliability. A 62-meter patrol vessel can exceed 32 knots, operate in shallow water, launch RHIBs, support crews, and maintain access to internal systems. For viewers, the useful idea is clear. Patrol speed has value only if the vessel can stay out, repair quickly, see at night, turn sharply, and keep people functional inside. The hard limit is daily readiness. Powerful propulsion and smart sensors mean little when maintenance access is poor or crew spaces exhaust operators before the mission ends or weather closes around them at sea for days offshore. Carrier flight operations may seem distant from aluminum ferries, yet they expose the same rule at a higher scale. Speed only matters when the surrounding system can absorb it. Aircraft launch and land because deck crews, catapults, blast deflectors, arresting gear, signals, checks, and timing all line up. One jet leaving the bow proves less than the repeated cycle behind it. The achievement is coordination under heat, noise, wind, and moving steel. For high-speed ships, the related lesson is reliability. The vessel must handle fast events without confusing the crew or overloading support systems around them during operations at sea. Enterprise's aft end superlift shows why naval speed begins in construction. Massive blocks have to land accurately before later systems can function. The carrier scale makes one point visible: heavy structure, routes for pipes and cables, maintenance access, and module alignment are locked in years before trials. Precision during lifting becomes performance much later, when aircraft, fuel, sensors, and crews depend on those buried pathways below decks. Carrier construction updates slow the pace and reveal patience behind speed. Steel blocks, outfitting, lifts, and internal systems advance in layers because testing later depends on access built earlier. The useful connection is sequencing. Complex ships earn reliability by leaving fewer hidden surprises for commissioning crews, sea trial teams, maintainers, and operators who inherit every early decision made inside the hull before propulsion finally proves anything offshore later. Replenishment at sea turns ship performance into a moving supply chain. Two vessels hold course and distance while fuel hoses or cargo lines connect across open water. Speed helps a fleet reposition, but endurance comes from transferred discipline, navigation, station keeping, pumps, communications, and trained crews working with narrow margins. Without resupply skill, fast ships become short-legged assets once fuel, food, and parts run down far away. USS America replenishment footage closes the military link. A ship stays useful only when supply can reach it underway. Fuel, stores, aircraft support, and crew endurance extend operational value. Fast movement opens options. Reliable resupply keeps those options alive after the first sprint ends, far from port for days ahead. So the useful question is no longer civilian or military. It is whether speed survives payload, crew workload, maintenance access, fuel planning, and the ordinary grind of keeping a vessel ready. So when is speed actually useful? Not when a number looks good on a brochure. Speed matters when the hull cuts drag efficiently. The material stays light without becoming fragile, and weight control survives every seat, cable, ramp, tank, pallet, and repair part added later. Francisco shows the commercial version. Shorten a crossing, keep passengers comfortable, protect schedule, and make fuel cost tolerable. EPF shows the logistics version. Move people and cargo quickly when ports are limited, ramps matter, and shallow draft opens access. LCS shows the more complex naval version. Over 40 knots has value only if sensors, maintenance, training, damage control, and reliability keep pace. The lesson across all of them is strict. A fast vessel is not fast because one engine is powerful. It is fast because hundreds of decisions refuse to waste that power. The hull, structure, water jets, fuel system, testing, and maintenance all protect the same goal, turning engine power into reliable performance year after year, not just on launch day. That is why giant aluminum ships are fascinating. They look sleek from outside, yet their real value sits in details most passengers never see. Trim angle, pump vibration, inlet flow, weld distortion, breaker layout, ramp strength, spare access, fuel safety zones, and access for tired technicians at 2 a.m. If you had to choose one factor that makes high-speed ships succeed during rough, ordinary service, not polished demonstrations, would you bet on hull shape, propulsion, weight control, or maintenance? Share your pick in the comments. End of the line for this one. Hit subscribe if you want the channel showing up when we cover the next mill, port, or piece of equipment worth a closer look. Take care.